This is part 3 of lecture 2.5 Mathematical Induction. In this video, we will introduce the principle of strong induction and learn how to use this to prove statements that hold for an infinite set of consecutive natural numbers. Recall that the principle of mathematical induction states that if a predicate P is true for the first natural number, and if for every natural number k, if P is true for k, then P is true for k plus 1, then the predicate is true for all natural numbers. The principle of strong induction is an axiom which is very similar to the principle of mathematical induction. The only difference between the PMI and the PSI is in the second condition in the hypothesis. In the PSI, this states that for every natural number k, if P of k is true for all natural numbers from the first natural number up to k, then P is true for the natural number k plus 1. All other parts of the statement of the PSI is the same as in the PMI. It can be shown that the principle of strong induction is equivalent to the principle of mathematical induction. The proof of a claim of the form for every natural number n, P of n, using the PSI has a very similar outline to a proof using the PMI. The basis step consists of the verification of the condition P of n for all natural numbers from the first natural number to some natural number r. The choice of the number r is determined by trial and error and depends on the arguments used in the inductive step. You will understand this better when we illustrate this in the examples which follow. For the inductive step, we let k be an arbitrary natural number greater than or equal to r, and assume that P holds for all natural numbers from the first natural number to the natural number k. This is our induction hypothesis. Our goal is to show that P holds for the natural number k plus 1 using the conditions in the induction hypothesis. A proof using the principle of strong induction is used when the statement P of k plus 1 cannot be proved by assuming P of k alone, but rather needs the conditions P of n for other values of n smaller than k. As an example, consider the following claim. Let a1 be the integer 2, a2 be the integer 4, and let an be equal to 5an minus 1 plus 6an minus 2 for every natural number n greater than or equal to 3. Then an is equal to 2 raised to n for every natural number n greater than or equal to 1. This is the claim in symbols. It is a conditional statement whose antecedent is the description of the terms an, and whose consequent is the statement an is equal to 2 raised to n for every natural number n greater than or equal to 1. Let P of n be the predicate an is equal to 2 raised to n. We begin the proof by assuming the antecedent of the claim. Our goal is to show the consequent. We shall do this by induction on n. For the basis step, we shall show that P of n is true for n equal to 1 and to 2. The reason for the choice of the number 2 will be apparent when we give the details of the arguments in the inductive step. For the inductive step, we let k be a natural number greater than or equal to 2, and assume that P of j holds for all natural numbers j from 1 to k. We need to show that P of k plus 1 holds, that is, that the term ak plus 1 is equal to 2 raised to k plus 1. We now show the proof. Assume that each term an is as described in the claim. We see that the term a1, which is 2, is equal to 2 raised to 1, and the term a2, which is 4, is equal to 2 squared. So the formula an equals 2 raised to n holds for n equal to 1 and to 2. This completes the basis step. Let k be a natural number greater than or equal to 2, and assume that aj is equal to 2 raised to j for all natural numbers j from 1 to k. Since k is greater than or equal to 2, k plus 1 is greater than or equal to 3. So by the hypothesis, the term ak plus 1 is equal to 5 times ak minus 6 times ak minus 1. Also, k minus 1 is greater than or equal to 1. So k minus 1 is one of the natural numbers from 1 to k. Thus, by the induction hypothesis, the condition P holds for both k and k minus 1. That is, ak is equal to 2 raised to k, and ak minus 1 is equal to 2 raised to k minus 1. Hence, ak plus 1 is equal to 5 times 2 raised to k minus 6 times 2 raised to k minus 1. We can factor out 2 raised to k minus 1 from both terms to get the expression 2 raised to k minus 1 times 5 times 2 minus 6. This is equal to 2 raised to k minus 1 times 4, which is equal to 2 raised to k minus 1 times 2 squared, which is equal to 2 raised to k plus 1. So ak plus 1 is indeed equal to 2 raised to k plus 1. This completes the inductive step. Therefore, by the principle of strong induction, an is equal to 2 raised to n for all positive integers n. Recall that the generalized principle of mathematical induction extends the PMI to a statement whose conclusion is that a predicate P holds for all natural numbers greater than or equal to a natural number m. In a similar manner, the generalized principle of strong induction extends the PSI to a statement whose conclusion is that a predicate P holds for all natural numbers greater than or equal to a natural number m. Its hypothesis is that P holds for m, and that for every natural number k, the condition that P holds for all natural numbers from m to k implies that P holds for the natural number k plus 1. To prove using the generalized PSI that a predicate P holds for all natural numbers greater than or equal to m, we need to verify in the basis step that P holds for all natural numbers from m to some natural number r. The choice of the number r depends on the arguments used in the inductive step. Next, for the inductive step, we let k be an arbitrary natural number greater than or equal to r, and assume that P holds for all natural numbers from r to k. This is our induction hypothesis. We need to show that P holds for the natural number k plus 1. As an example, consider the claim any integer greater than 33 can be written in the form 4x plus 5y, where x and y are integers with x greater than or equal to 3 and y greater than or equal to 2. Since the condition greater than 33 is equivalent to greater than or equal to 34, the claim is equivalent to the statement for every natural number n greater than or equal to 34, there exist integers x and y such that x is greater than or equal to 3, y is greater than or equal to 2, and n is equal to 4x plus 5y. Let P of n be the predicate. There exist integers x and y such that x is greater than or equal to 3, y is greater than or equal to 2, and n is equal to 4x plus 5y. For the basis step, we will show that P of n is true for n equal to 34, 35, 36, and 37. For the inductive step, we let k be an arbitrary natural number greater than or equal to 37. We assume that P of j is true for all j from 34 to k. We need to show that P of k plus 1 is true. That is, that there exist integers r and s such that r is greater than or equal to 3, s is greater than or equal to 2, and k plus 1 is equal to 4r plus 5s. We now show the proof. Observe that 34 is equal to 4 times 6 plus 5 times 2. 35 is equal to 4 times 5 plus 5 times 3. 36 is equal to 4 times 4 plus 5 times 4. And 37 is equal to 4 times 3 plus 5 times 5. Each of these numbers is written as a linear combination 4x plus 5y, where x is greater than or equal to 3 and y is greater than or equal to 2. Hence, the condition P holds for the natural numbers from 34 to 37. This completes the basis step. Let k be an arbitrary natural number greater than or equal to 37. Assume that each natural number j from 34 to k can be written as 4x plus 5y for some integers x and y, with x greater than or equal to 3 and y greater than or equal to 2. Since k is greater than or equal to 37, k minus 3 is greater than or equal to 34. So k minus 3 is one of the natural numbers from 34 to k. Hence, by the induction hypothesis, the condition P holds for k minus 3. That is, k minus 3 is equal to 4x plus 5y for some integers x and y with x greater than or equal to 3 and y greater than or equal to 2. Hence, the natural number k plus 1, which is equal to k minus 3 plus 4, is equal to 4x plus 5y plus 4, which is equal to 4 times x plus 1 plus 5y. Clearly, x plus 1 and y are both integers with y greater than or equal to 2. Since x is greater than or equal to 3, x plus 1 is greater than or equal to 4. So x plus 1 is also greater than or equal to 3. Thus, we were able to write k plus 1 as a linear combination 4r plus 5s, where r is greater than or equal to 3 and s is greater than or equal to 2. This completes the proof of the inductive step. Therefore, by the PSI, every integer greater than 33 can be written as 4x plus 5y for some integers x and y, with x greater than or equal to 3 and y greater than or equal to 2. You have come to the end of part 3 of lecture 2.5. Before you proceed to the next lecture, you are strongly encouraged to answer the exercises at the end of these slides. Thank you for your attention.